Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at modelling with parametric equations so we can answer questions from exercise 8e. Modelling meaning solving real-world problems. So, a plane's position at time t seconds after takeoff can be modelled with the following parametric equations. X equals v cos theta times t and y equals v sin theta times t, where v is the speed of the plane, theta is the angle of elevation of its path, and x is the horizontal distance travelled, and y is the vertical distance travelled relative to a fixed origin. When the plane has travelled 600 metres horizontally, it has climbed 120 metres, and the first part of this problem is to find the angle of elevation. Well, let's draw out a little diagram. We've got horizontal elevation of 600 and we've got vertical elevation of 120. So a little bit of right angle trigonometry here can give us tan minus 1 of 120 divided by 600. So we get 11.3. Note that this model is assuming that the plane's angle of elevation remains constant. It doesn't go up and then down by any amount, or the elevation doesn't go up and then down, it goes in a straight line. So 11.3 is that angle of elevation we're looking for. Given that the plane's speed is 50 meters per second, find the parametric equations for the plane's motion. That just means plug in the v and the theta values into your parametric equations. So if x equals v cos theta t, then substitute in your v value and your angle of elevation, 11.3, and you're going to get x equals 49.0 t. And do the same for y. Y equals v sin theta t, substitute in your two values for v and theta, and we're going to get y equals 9.8 t. Okay, so there we are, that's not too bad. Part C of this question is to find the vertical height of the plane after 10 seconds. Well, that's just substituting 10 into the correct equation. Is it in seconds, this question? Yeah, do just make a quick check to see if the units do match up there. If it was 1 minute, you'd have to convert that into 60 seconds, and you wouldn't want to have accidentally substituted in 1 by accident. So y is the vertical height. Substitute in the value of 10, and we're going to get 98 meters. Okay, part D is show that the plane's motion is a straight line. To do this, you need to find the equation of the plane's motion in Cartesian form and show that it is linear. So what we're going to do is we're going to rearrange one of the formulas, substitute it into the other formula just like we have done in a previous video to work out the Cartesian equation, and simplify, and we get y equals x over 5, so therefore the plane travels at a gradient of 1/5 from the origin. Part E, explain why the domain t is greater than 0 is not realistic. This would mean that the plane continues climbing indefinitely at the same speed and with the same elevation. It's obviously going to get to a certain altitude and then stop its vertical height inclination. So in this case here, maybe t should have an upper limit of maybe 600 seconds or 1200 seconds. Okay. Alright, so let's move on to a second variety of these modelling with parametric equations. In this case, a stone is thrown from the top of a 25-metre high cliff with the initial speed of 5 meters per second at an angle of 45 degrees. Its position after t seconds can be described using the following parametric equations. X equals 5 root 2 over 2 times t, and y equals minus 4.9 t squared plus 5 root 2 over 2t plus 25. X here is the horizontal distance and y is the vertical distance from the ground. Given that the model is valid from the time the stone is thrown until it hits the ground, find the value of k. So k here is in the limit, and we want to find that value of k such that when it hits the floor, given that the time is valid until it hits the ground. So what are we going to set? We're going to need to set the y coordinate equal to 0. We want the elevation to be 0. And now we're just going to solve this. So setting that equal to 0 using your quadratic formula, substituting the values in, or you could just use the polynomial solver on your calculator, and you will get t equals minus 1.92 and 2.648. But we don't want negative time, so we'll just cross out that solution there. So the answer here is 2.648. So it's going to take 2.648 seconds for it to reach the ground. Part B is find the horizontal distance travelled by the stone by the time it hits the floor. So substituting in 2.648 into the x equation, and this is going to be a linear relationship, times it by the 5 root 2 over 2, and we get 9.36. So it will have travelled 9.36 metres once it's been thrown off the roof. Okay, that's the second one done. Now we've got a third question to do here. The motion of a figure skater relative to a fixed position O at time t minutes is modelled using the parametric equations x equals 8 cos 20t and y equals 12 sine 10t minus pi by 3, where t is greater than 0. X and y are measured in meters, and this is what the diagram looks like. So a very nice figure of 8 here, slightly crooked to the left, but that's absolutely fine. The figure skater can do as he or she wishes. So let's have a go at answering the questions here. Find the coordinates of the figure skater at the beginning of their motion. So that's nice and easy. Plug in t equals 0. T here is measured in minutes and not measured in seconds. So plug in t equals 0, and we're going to get 8. And we're going to plug in t equals 0 into the y equation, and we're going to get minus 6 root 3. So effectively this is like a coordinate. 8 minus 6 root 3, so 8 along the x-axis, minus 6 root 3 along the x-axis, somewhere in the bottom right quadrant. The next question here is to find the coordinates of the point where the figure skater intersects their own path, given that it takes place on the x-axis. So we want to find this intersection point here, the one that's growing. What we'll have to do there is, given that it happens on the x-axis, we want to set the y equation equal to 0 to find the t values, and then we can substitute the t value into the x equation. So given that it's intersecting the x-axis, we set y equal to 0 and solve the equation. So divide through by the 12 at the start, set the 10t minus pi by 3 equal to 0, move it on to the other side, divide through by 10, and the first time this is going to happen is at t equals pi by 30. Note that in some cases you might need to use your knowledge of trig equations to find more values of t. In this case here we won't, because we've got t is greater than 0, this is greater than 0, so it follows the domain for t, and it's going to be where we intersect the y-axis. We don't need to necessarily show it's going to come round and loop back onto itself again. So plugging in t equals pi by 30 into the equation, we're going to get 8 2 pi by 3, which will give you minus 4. So the coordinate that it links back onto itself is the coordinate minus 4, 0. Just remember that you can use these parametric equations to represent coordinates. This one will work out the x-coordinate, this equation here will work out the y-coordinate. Part C is to find the coordinates of the points where the curves intersect the y-axis. Well, if it intersects the y-axis, we'll have to set x equal to 0. So in this case here, cos 20t is going to equal 0, so inverse the cos, and we'll get 20t equals pi by 2. And let's find some more values that it will intersect at. So we need 4 more. It's going to be pi by 2, 3 pi by 2, 5 pi by 2, and 7 pi by 2. By the time it's got onto the next one of 9 pi by 2, it should be looping back onto the same one that it was at pi by 2. So divide through by 20 and these will give us our t values. Just make a note that you should find the 20t equals solutions before you divide everything by 20, rather than dividing the first solution by 20 and then finding more solutions from there. So find the extra solutions at this stage. Right, so now that we know these values here, let's substitute them into the y equation, and we're going to get minus 3.11, 11.59, 3.11, and minus 11.59. So that would kind of make sense. It's all very symmetric. So the figure skater starts down here, goes this way, then this way, then this way, and finally back round to the bottom after. Okay, next question then, part D. Find how long it takes the figure skater to complete on the figure 8 motion. So the skater will have completed a full figure of 8 when both his or her x and y coordinates are in the original position. It is possible that the x coordinate will return to its starting position, but the y coordinate being different. If we take x equals cos t, the graph of cos has period 2 pi, so the skater would return to their original x position every 2 pi minutes. The period of the graph is determined by the coefficient of t. So in this equation here, when we have the equation x equals 8 cos 20t, this graph of cos has period of 2 pi by 20, so the skater would return to their original x position every 2 pi by 20 minutes. But we're going to have to do the same for the y equations as well. Y equals sine t has a period of 2 pi as well, but the coefficient is going to signal to you how often it's, or be the multiple of that periodicity. So the graph of sine has a period of 2 pi by 10, so the graph would return to its original y position every 2 pi by 10 minutes. That's because we've got this effectively like a scale factor multiple on the t value. So the period is going to happen 10 times as often effectively, because we've got this scale factor of 10. So these values are going to be 2 pi by 10, 4 pi by 10, 6 pi by 10, etc, etc. So what we'd like is for the original x coordinate and for the original y coordinate to be back at the same position, and it looks like this happens at 2 pi by 10. So the figure of 8 takes place every 2 pi by 10 minutes, and then converts that into seconds, and we get every 38 seconds. Okay. Right then, your turn to have a go at this question here then. Pause the video and try this one out. Okay, so question 2 here, the position of a small plane coming into land at t minutes after it has started its descent is modelled by the parametric equations x equals 80t, y equals minus 9.1t plus 3000, where x is the horizontal distance travelled and y is the vertical distance travelled from the point of starting its descent. Find the initial height of the plane. Well, that's nice and easy. We just plug in t equals 0 into y, and that's going to give us 3000 meters. Justify the choice of the domain from 0 to 329 for this model. Well, we don't want it to go into negative. We don't want it to go into negative height. So what we want is to set the y equal to 0. And then we're going to get minus 9.1 t plus 3000 equals 0. So therefore t is going to equal 3000 divided by 9.1, which is going to give us, is it going to be that number exactly, or is it going to be a little bit less than it? 3000 divided by 9.1, which gives us 329.67. 329.67. So yes, it definitely makes sense. Justify the choice of the domain. The reason being is that because we don't want negative height above the ground. Okay, that's the answer to part B. Find the horizontal distance the plane has travelled between the beginning of its descent and landing. So, effectively what we'll do then is we'll plug in t equals 329. T being in minutes, 329 minutes, that's quite a long time. Anyway, x is going to be 80 times by 329. So in this case here, it's going to be 80 times 329, which is 26320. So that's going to be 26.32 kilometers. Okay, so that's all we have for this question here then. So have a go at plenty of the other questions from exercise 8E. Have a go at the ones with a P next to them for problem solving questions and the E for the exam style questions. Persevere through the difficult ones and ask your teacher for help if you need any. Thanks for watching.